Kind of like, I'm going to zoom in really quickly on one specific part of state channels just to like kind of set the understanding of how state is progressing a state channel and generally what it is. And then I'm going to zoom out afterwards and just talk generally about the project that we're working on. And yeah, hopefully give you a general overview of like what's going on with state channels. So yeah, and then also I would encourage you, if you're following along and like you don't get something, it makes no sense, or you're just curious about something else, just raise your hand and we can make this interactive as well. So yeah, let's get started. So yeah, this is just outlining what I basically just said. We're going to talk a little bit about the life cycle of a channel really briefly, just so we're on the same page. The state progression protocol, some components that you actually need to make any of this stuff work for anybody in production, and then what's going on today, and then what are we doing in the future. So ELI5 state channel life cycle, just so that we're on the same page. Here's like the easiest way that I can explain a state channel in like a nice graphic, if the animations work. So state channel ELI5. You got two people, let's call them Alice and Bob, and they have some coins, and the idea is what you want to do is put some coins in a contract, so you lock them up for some amount of time, and then off-chain send messages to each other updating the allocation of those coins. So like let's say that there's 5 there on each side. At the beginning there's 5, 5. And then Alice says, hey, now actually at the number 2 version of this, now it's actually, well actually it's still 5, 5 in this example. Then it's 4, 6 at number 3. And still 4, 6. And you do this over and over and over and over and over again until, let's say you're done this like 98 times. And now you have like 8 for Alice, 2 for Bob. And all this stuff is just like messaging. Like they just sign messages back and forth, off-chain, there's no transactions, nothing like that. And at some point they're like, okay, we're done here, we've moved our money around, we're happy with what's happened, 8 for me, 2 for you, great. And so they take the latest version of this, tell the chain, hey, this is the allocation. Worst case, if you need to, there's a timeout to ensure this is the latest version of it. The contract says that's true, and then dishes out the money. Okay, so level setting. That's basically what a state channel is about. Off-chain, updating state without using the chain. At some point later on, you put the latest version on, or equivalently, you tell the chain what the latest outcome is, and then the money gets distributed back out on-chain. The nice perk, obviously, is it's instant, all these messages, and you don't have to worry about confirmation time, stuff like that. So that's state channel. So I'm going to now dive deep very quickly into specifically what is the standard around which you actually update that state. So you saw like, version 1, version 2, version 3. I'm going to talk very quickly about specifically what that protocol looks like. So let's talk about what's actually in the state of, in the state channel. What are you actually storing? And there's a bunch of fields, and I'm just going to say in English what each field is, and you can kind of get a bit of an intuition for what's actually being exchanged in each one of those back and forth boxes that are signed by each person. So these are pretty straightforward things. I'm going to just go through them, but they're pretty straightforward. Obviously, you need to know who's involved. In a state channel, you have a fixed group of people. It's like Alice and Bob is 2 fixed group of people. Maybe you have Alice, Bob, Charlie. That would be 3 fixed groups of people. And you need to know who those people are. You need to know what chain you're on. This is pretty straightforward. You're in mainnet, or in Rinkeby, Robston, whatever. You need to know also some unique identifier for the channel. So in that one example I just gave, that was like some payment channel. Let's say it was the unique identifier of just anything at all. This is just to make sure that you can't replay the same channels over and over again. You need to know how long of a challenge period is this channel going to have if you need to go to chain. You want to know what version number is it. Again, this is pretty straightforward stuff. If you're going back and forth over and over again, each time you hop, Alice signs, Bob signs, Alice signs, Bob signs, you increment some number. So you have a latest version number. You also have this notion of the outcome. So I just gave you an example earlier where it was like Alice had 4 and Bob had 6. That was both the outcome and the state in that example. But in a more complicated example, you might imagine the state being something, let's say like a tic-tac-toe board, and then the outcome would be who would be the winner. So you can imagine in a game of tic-tac-toe, if the state is a state with 3 X's in a cross, then the winner is whoever is player X, and the outcome would be such that they get like 10 coins and the O player gets 0 coins. So the outcome, and then you have the state, and you want to store the outcome at each state. Additionally, you want to know, is this a final state? which is obviously in tic-tac-toe, it's like, hey, is this a cross? Is it a vertical cross, or is it still a game that's in motion? So this is also something that each one of these states has. And then you want to have the actual definition of the state machine, like what's going on. Is it this tic-tac-toe game? Is it a payment channel? Is it a backgammon game? Is it roulette? Whatever the actual thing is which defines the state channel. And I'll show some function which explains what that looks like. And then this application specific data. So this is like literally like where are the X's and the O's in the tic-tac-toe board? What are the actual values of the application? So yeah, and then obviously the signature for each person. So this is like pretty specific, right? I mean, I literally went through every single list of the fields in a state channel. But I think it's useful to keep this in mind that every single time you pass a message back and forth between people, all of these bits of information are encoded within the message that's sent. And this is the standard around which we've basically gotten now within our state channels kind of community for every state update. So yeah, it's pretty specific, but it's pretty useful to kind of just generally keep in mind that these are the specific fields that you store. So great. Here it is, the same thing I just said, but encoded with some data types for your own reference. You can see it's pretty straightforward what each type represents. And you can also notice that these things are actually, you can kind of split them. Some are fixed every state update, so you can see, for example, the list of participants always stays the same. The chain ID stays the same, obviously, the unique identifier, the definition of the application. But some things change, right? The tic-tac-toe board state will change, the signature changes, and again, it's just useful to keep in mind what each state has. So another interesting component of the state channel protocol that I've kind of glossed over, but it's kind of unique to the way that we've designed the system here, is that each state is signed by just one person. And the way that it works is each state has a particular person that's expected to sign it. And you can use this formula to calculate it. It's basically the participant at the index of the turn number modulo the length of participants. So this kind of fancy way of saying you take turns. Alice, Bob, Alice, Bob, Alice, Bob, Alice, Bob. You keep going in a cycle. And if it was 3 people, it's like Alice, Bob, Charlie, Alice, Bob, Charlie, Alice, Bob, Charlie. And each state, again, is signed by just one of those people. And it's exactly one of those people that's expected to sign each state. And this is also important for a number of reasons I'll get into, but basically this means that you always know who's expected to sign the next state, which means you can force somebody on the chain to make the next move, to sign the next state. And if they don't, and the timer passes on chain, you know that that person basically forfeited their chance to progress the state. Some other stuff, this is pretty straightforward, but obviously it has to be your turn if you're going to sign the state. You can't sign some other person's state. It should go without saying, but this is just an explicit way of showing that you can't sign some other person's state. And then the nice part of this system also is that you can exit at any point in time. If you're done, you don't want to play anymore, you can say, this is final, I'm setting this final flag to true, I'm done. And if the other person also signs this final flag is true, then you have 2, or more generally n, sequential states where they all say this is final, and so you can basically consider this to be a conclusion proof until this channel will be done. And again, an important part of the system that I mentioned is that you sign the outcome at each state, which means that at any point in time, the protocol could break, and whatever the last state is that was signed needs to encode who gets the money. So an example with tic-tac-toe is if I just placed my X, the outcome is such that I win. And this is interesting because it means that if no O is ever placed ever again, that basically means that O is forfeited, they've left, and so it should make sense that I, X, as the last person that made the move, should be considered online, available, and I should be the winner. So you encode the outcome at every step of the way. At no point is there some limbo state where it's not clear who gets money. Every single state encodes it. And so you can see that also means that if you want to just like exit, you can exit. And this is basically equivalent to forfeiting in this case. So again, these are pretty specific points, pretty simple points, but shockingly, these are the types of things that trip people up when they start to really think about channels and they try to understand what happens in every scenario. The other part of the whole system is that we have a very simple way of encoding what is a valid state transition. And that is basically, literally, we have a function called valid transition between any 2 states. So 1 and 2, 2 and 3. And a state transition is only valid if the definition of the state machine, which I alluded to earlier, has this function valid transition for which the 2 subsequent states when passed in, return true. So most basic possible example is like a counter. How do you write a counter app? Here's how you do that. The counter is an application where every time you update the state, you just add the number 1 to whatever the last counter was. So you can see here, if I can use the red dot thing, counter 0 is good, 1 is 1 more than 0, 2 is 1 more than 1, so this is a good transition. But this is a bad transition because 5 obviously is not 1 more than 1. So you can encode literally any arbitrary, pure solidity code, or more generally speaking, like a static function that you can run in the EVM using this general function. And there's also nice ways of encoding this so that it looks prettier, so you can write like action-based function signatures. But generally speaking, you just need this function to return true. And that allows you to write any arbitrary state machine in Ethereum for which you can fit this within one block. So again, pretty straightforward, but this is exactly how you write an actual application for state channels. Great. So that was the zoomed in part. Very quickly, I said, okay, here's exactly how you update state. This is one part of a much broader system. And that system is this. Generally speaking, this is like the set of all stuff you need to kind of think about when there's in state channels land. And I just spent like 10 minutes talking about, to be honest, at a pretty high level even still, the state progression protocol. So the reason I'm talking about this stuff is I want to try to convey a bit of information about what are all the things you have to think about in state channels and how they can very quickly get complicated, and hopefully give you a bit of intuition for when you're thinking about the overall system, what you can like Google or go to learn more about. So I just talked about this. There's a lot more docs and there's talks online that go into a lot more detail. Now I'm going to give you a bit of context on what's going on with all the rest of this stuff with our overall work. So let's dive into that stuff. I break this down to 3 categories. One is the actual protocol and contracts, like the cool cryptography stuff. Then there's the client and hub, which is more of the engineering challenges that are involved with building a state channel system in production, which is like the software that implements all of this stuff, and both for the client, the users, if you're in a browser, phone, whatever, and the hub on the back end, and that's facilitating some of this work. And then the browser wallet UI, UX, all the other cool stuff that you need to think about when you're building an actual end user application. So I just talked about the state progression protocol. Like I've said, that's this thing. You take turns, you sign states, one signature, that's an app definition, so on and so forth. But what's this thing? There's also a whole other protocol for how you fund those channels. So I abstractly just mentioned a second ago that you have some channel with some money in it, and you progress it using the general protocol I described. But how do you actually get money to be assigned to a particular channel? It kind of makes sense if you have one contract being one channel, right? Because you just put money into the contract, and there's like a deposit and a withdrawal, and it seems fairly straightforward. But it gets a lot more complicated when you wanted to put money in one time for some set of people and have many channels, perhaps running in parallel, maybe thousands of channels at the same time. And so for this, we have a protocol. We call it right now the Nitro protocol. You can go to our repo, which I'll show in a second, to look at this in a lot more depth. But this is the other part of the system. And we have this now completely specified and implemented. And this is where it gets a lot more complicated. This is a picture from the paper that defines, roughly speaking, how you go from having a contract with A and B having 5 and 5 to going through this protocol that we define. You don't need to understand what these pictures mean exactly. This is just from the paper. To a situation where you have a channel now with some money allocated to it. And this protocol, we're going to hopefully do some formal verification on later this year. Then there's the part above that, which is what exactly do 2 people say to each other to actually operate this protocol. And so for this, we have defined an exact protocol between some number of participants through a hub of precisely which message is sent to each other participant in order to fund a channel. In accordance to this general protocol, which is like the mathematical description. And again, this is online as well. You can check it out, and I'll share some links at the end. This is the other part of a state channel system you kind of need to be aware of. The part on top of that is actually the code that implements it. And this is like where the engineering part gets quite fun. This is what we call kind of a state channel client. We've designed ours to run in the browser. It's pretty interesting software because it needs to both implement this protocol in accordance to this overall design, and work in the browser, store state on behalf of the user, make sure it doesn't drop state, and all these things. And then finally, once you have some software which implements all of that, the next thing you need to think about is how do wallets, like a MetaMask, actually use it in such a way that dApps can communicate to their wallets to take advantage of channels. And so there's a picture I've added which shows roughly what the API looks like as of today between an app, let's say like a browser window, and a wallet, let's say MetaMask, to how they communicate to one another. So you can imagine, like an example, an application might say, hey, I want to create a channel. So it sends a chan_create message in the same, it's kind of similar to the way that Web3.js works, if you're familiar, into MetaMask. MetaMask is running the client code that I mentioned, and MetaMask is expected to basically follow the protocol exactly as specified using that software, and then return back to the app saying, hey, the channel's created, and now you have this new object to use in your application. And so this is a whole other domain which is interesting, and a lot of interesting problems to work on here. And then if you're interested in just purely the design aspect, there's also like a whole bunch of questions about what does an end user actually look at when they're looking in the browser at an application with channels. So I think this video should play. Here's the Connect die card UI. To be honest, it's kind of boring, which is probably good for UI of this stuff, but it allows you to send money instantly with no pop-ups. You just click a button and some payment happens. And what's going on in this GIF is basically, and I'll play it a second time, is basically a message is being sent into the wallet runs the code to run the protocol I showed earlier. Message gets sent to the other guy, signature on the state showing that I want to update what the state of the application is, and then a payment is made, and you can see that the UI in the end of the day is pretty basic. So yeah, this is like the full stack of state channels. Very quickly, just kind of giving you a broad idea, like when we say state channels, what the hell is actually happening? It's all of those problems all bundled up together. Great, so now I'm going to jump a little bit over into specifically some updates from us on our team that we've been working on. So the first thing is it all works, which is an amazing accomplishment. This stuff actually is today on mainnet. The most I guess notorious example is that the Connect company is currently running that exact application I just showed you on mainnet with payments going through their users on the die card application, which is what I just showed. And they're trying to build a bit of an ecosystem around this. So they're trying to get some applications to build on top of them, and they're basically running a client on top of our client at the moment. They're trying to get some infrastructure built on top, so connecting into Infura and to Matic Network, and they're trying to integrate into wallets. So we've already done some work with MetaMask, they're working with a bunch of other wallets, and we're trying to build a bit of an ecosystem around the state channels protocol. And I think I have a tweet, yeah, and this is literally yesterday, actually. He did a proper announcement, after we ironed out all like the bugs and whatnot, saying, hey, this stuff actually is live right now, you can use it today. So if you guys want to, you can just like Google Connect die card, and you can see all of this software running under the hood. So that's like the first nice update. This stuff's on mainnet today. The second thing is we're growing the team. So one thing that we've been doing in the state channels world over the past little while is we've noticed that there's many teams all working on the same stuff, which maybe you guys have noticed, especially people that work in this industry. Like there's a lot of overlap in this industry where people will do the same work, and so we've tried very hard to try to create standards. And the protocol I showed earlier is the standard state progression protocol across all state channels teams right now. And so one example of that manifesting is recently the open source project, which I didn't really discuss so much in this talk, Counterfactual, has merged with this company called Magmo, for which we've been running 2 separate protocols for state channels. And we're launching this new project called statechannels.org. And there's a bunch of people now, which is pretty awesome to see, like across multiple different companies all working on this open source together, which is great. You can see us on the internet, github.com/statechannels. There's like, I think now is about 10 people working across the stack on the wallet integrations, on the protocols, on the contract itself, on formal verification of these things. There's a lot of cool problems being solved across our teams. And this is actually like a pretty awesome accomplishment because, like I mentioned, there's been so much redundant work in this industry, and now we're really starting to get into a stride with a single implementation and a single standard, which is great news. So great. So what are we actually working on now? What's like the next stuff that we're focusing on that's of interest to us right now? Here's the stack to reiterate. Within each section, here's like some stuff we're doing. So for the protocol and contract side, we are doing, like I alluded to, some formal verification of the actual state progression protocol. So we want to guarantee this property. At any given point in time, any participant will be able to basically exit their money in a fixed amount of time. So this sounds like, a pretty straightforward property of channels, but you'd be surprised, like, I don't think any channels construction anywhere has this, maybe Lightning, but especially in Ethereum. So we spent a lot of time actually modeling the protocol that we've come up with. We used a tool called TLA+, which is very useful for finding weird edge cases in your protocol for which this property might not hold. We even found some bugs where you can get into front-running scenarios where one person observed the transaction being put on chain and the other will then try to basically front-run that with a different transaction, causing an error. And it gets pretty hairy, but we're trying to really harden this protocol so that you have an absolute guarantee that anything that follows this protocol will not lose you money, and specifically will have this property. So this is the nice benefit of standardization as well. It actually pays off to do this kind of work because we're certain this is going to be the standard state progression protocol. Other stuff we're doing is that we now have a research forum. So if you're interested in any of these things, we have a forum now. The website is research.statechannels.org. You can go there. We have all the people in the state channels world checking this thing, getting email updates. So if you have a question you want to ask or an idea or something you want to poke a hole at in the protocol, we're now more actively iterating on it. So we're kind of creating our own separate state channels world outside of the pure Ethereum world, where we can start discussing and coming to conclusions on technical details of the protocols. This is also a pretty cool thing. Another thing that we're doing is we're making this stuff wicked fast and wicked cheap. So you can see we did a full deep dive into the contract code that we had for running this protocol in the past month and a half or so, and we reduced the costs dramatically for both the happy path and the challenge path of a channel. So you can see in the happy path now, it used to be quite expensive, and now I think we've got it down as small as you can possibly get it without just doing inline assembly, to about 165K gas for any number of channels, which is pretty good. And then the challenge path is something goes wrong and someone challenges you on chain, you can respond and get your money out with 200K gas, which is reasonable at this point, I think, for something of this nature. So that's another thing we've done. And we're also documenting everything. So you can see that we have a website. It's not actually live on a public URL yet, but this stuff's all open source on our repo if you want to dig into it and just run it yourself. But we're going to put this up later. A full protocol description of exactly which messages gets passed between each person, the exact rules, the motivation behind all of it. And this is also something that we're trying to get out by the end of this year in such a way that I could share this with all of you and it would make perfect sense how it all works. So a lot of documentation. I think we talked about in the panel yesterday the importance of documentation, so hopefully this becomes useful to anyone interested. Client and hub. So one thing that we're doing is I mentioned earlier that we have an implementation. That's version 1, that's what Connect is running. We're now creating a version 2, which we hope will be the go-to implementation for anyone here that wants to use it for state channels. And there's a couple of properties that we're aiming for. So one is we do store all of your states right now, but it's kind of a bit janky. It's stuck in local storage. We don't have exact guarantees that you don't accidentally lose some of that. So we're trying to make it be the case that we can guarantee you're never going to lose any state. We're going to automatically detect and respond to challenges that might occur between you and a hub, you and any other counterparty in any part of the protocol. And we want to make this, like you mentioned, the go-to production quality software for hubs, if you want to run a hub or for a client, such that any wallet can implement this. And that's what we're doing now. And then finally in the browser and wallet UX, we're also doing a bunch of research into what exactly should a browser show for channels. So there's a bunch of open questions here. One is how do you interact with a state channel? Like I showed one example in that GIF earlier. One is how do you actually get consent from a user? Because if you have more than one channel, you don't want to have a pop-up every single time. How do you trust the actual application that you're running? It could be the case that the application code is just bad, in which case you're just basically trusting some Solidity code that will just lose you money. So how much trust does the user need to have in the actual app? To what extent is the wallet going to actually protect you? And what policies, which I'll show a picture of in a second, should the wallet actually be able to enforce? So one example of this is we have this idea right now of a budget per tab in the browser. We're working with MetaMask on this right now, and we also have a demo that we're going to try and release in the next few months, which which encodes this general idea, which is when you go to a tab, the wallet will ask you how much money do you want to allocate to this tab. And then what you're doing is essentially saying this tab can open and close an unlimited number of channels for any number of reasons up to this amount. And the wallet software will basically enforce that. So here's like one idea of like how we're looking at this from a UX perspective. So again, I'm going pretty quickly through a lot of different topics, but the point here is to show that this is a big area with a lot of open problems and interesting things to work on. So yeah, I think that's it. If you're interested in generally keeping up to date with what we're doing, this is our Twitter, it's @StateChannels. There's an enormous number of problems, like I've kind of been saying, and yeah, thanks for listening.
Thank you very much. Do we have any questions from the audience? If you have any questions, please feel free to raise your hand. Any questions?
You mentioned that there's a bunch of applications live on mainnet. Could you recommend some to sort of play around with and investigate more?
Applications to play around with? I think so there's a couple things you can do. Yeah, the one that you can go to right now on your browser is at ttt.magmo.com. There's like a tic-tac-toe application. It's not following exactly this protocol. It's more of an older version, but it shows the general workflow of how you deposit money into a contract, play tic-tac-toe off-chain, and then get some money out. If you want to use the exact most up-to-date stuff, it's less of a fun app, but you can use the Connect stuff, so you can make payments. One thing that they've built using this is actually pseudo offline payments, where you can basically give someone a claim on some money that either you can claw back if they never take it, but they can also claw towards them and make it so you can't take it away. So it's like an offline payment in a way, almost like a gift card. That's an application that they have in their DAI card right now. I would say probably, yeah, the latest stuff, you should try the DAI card. Otherwise, if you just want to toy around with it, you can go to ttt.magmo.com. There's also a rock, paper, scissors one, I think, rps.magmo.com. Those are the more like for fun, like just generally get an idea of it stuff. We do have an application we're building. We haven't really announced it yet, but it's, yeah, I guess I can mention it briefly. We're trying to build an application right now where you can download and upload, so basically seed and leech arbitrary files using the web torrent protocol, where you have in the browser several concurrent virtual channels. So you and some other persons, if you're downloading, you're connected to like maybe 10, 15 people that are uploading, and you're paying them per byte. And so we actually have an MVP of that thing locally in our repo, and we're just trying to like get that thing working such that we can release it later this year, hopefully maybe super early next year. And the idea is that it'll include that policy UI I showed, and hopefully it'll encode all the things I talked about in like a really cool demo that actually like is useful for something, because you can then get paid to upload files, and you can also pay to get files, hopefully faster than using the regular web torrent application.
Wonderful. Do we have any more questions from the audience?
Yeah, so the fun like example is ttt.magmo.com, and then the production software is I guess connect.network. I think the website is actually DAIcard.io. Maybe someone can correct me. I don't know the exact website for the DAI card, but DAI space card. If you Google that, I'm sure you'll find it.
Okay, we'll take one more question. Okay, so anything else you want to add? About the...
Yeah, I don't know. I guess like the most important thing is like if you're interested in this stuff, there's a research forum you can go to. You can ask questions. The repo, github.com/statechannels, has not perfect documentation, but it's at least tractable. You can go in, you can add an issue, you can check out the code. It's we're progressively moving forward with a big team on this stuff, and so if you want to contribute or just ask a question, we're all available. And yeah, the goal is just to make this stuff work and make it coherent and tractable for everybody in one package versus in many disparate separate packages.
Great. Well, thank you very much for your sharing.
Thank you.